Okay, so welcome to the third part. If you start a movie series, you can't just stop with a sequel. You need to have a trilogy, or in this case, a thrilogy, in order to really feel like you're getting your money's worth, right? To bring closure to everything, etc. And this is no exception. So we saw in the first video how you could do linear regression line, and last time we saw how you could fit a polynomial, a quadratic at least. That we're going to do here is just to show you exactly how much stuff you have now, how you can model all sorts of things using the theory that we set out, right? I mean, you can imagine that once you see how to do quadratic, you can figure out how to do cubic, quartic, quintic, and all the other ticks that follow that. And, the computations get a little bit more complicated because, as the size of that polynomial grows, the size of the normal matrices, x transpose x, grows as well. It would be n by n for an n-degree polynomial, but still you're getting, you have to work a little bit harder, but you get something really, really powerful. So what I want to do is two examples to really show you the things that you can now do. Okay, and so we'll start with the same set of points, and we will try to fit a couple, or at least one more curve to this. And once you see this example, you see the sky is the limit here. And so let's look at a model like what follows.
Okay, so the points are at the top for your amusement. Try to find the best fitting curve of that form, y equals beta naught 2 to the x plus beta 1 to the x squared. If you understand the theory of what we've done, you should be able to do this. Okay, so notice it's kind of long in fine print, but it's the same exact thing. You start by getting equations that if the points perfectly fit that curve, that they would satisfy. And then you find the normal equations, you do your x transpose y, you do your x transpose x, and you find the best fitting curve. And so there you go.
Okay, and so if you look at the graph of the best fitting curve, it looks like this.
Now you can see this doesn't do a particularly good job of approximation, but unlike polynomials, there's no guarantee that this would be better. It suggests that maybe you shouldn't be using this type of curve to model this data. And frankly, I agree.
Once you see that you can do this exponential e type of thing, I mean, you can do sines, cosine, if you can imagine the function and you can compute its values, right, you can do this type of behavior. Okay. So now you can have these arbitrarily long strings of objects. You can't get too carried away. You can't do something like cosine of k or beta 0x or something like that, unless you want to start getting do some serious trig identities. But you can't quite do that. But you can do a lot of different things here. You can fit all sorts of sine, cosine, e, natural log. If you can imagine it, you can have it in there somehow, right? Well, if that's not enough, and it really should be enough if you can see all the stuff you've learned today, you can also use this in kind of a higher dimensional case, right? So here we've been having one variable y depending on one independent variable x, okay? But it turns out that life is often a function of several variables, that you have many independent variables, all of which have a response attached to it, okay? And so let's consider the following problem.
I'll let you read through most of this, but essentially what's happening is that the GPA, G, depends on two variables here, and so the variables that I chose were S, the number of hours spent studying per week, and B, the amount of bribes that she gives. You will notice down at the bottom there's that picture with salt, and there's a grain of salt, which is exactly how you should take this. Don't haul me into the dean's office because I'm making jokes about bribing your professor. It doesn't work. Anyway, so you can read the details. You have some data points there. And so what we want to do is we want to use the ideas that we've already developed to approximate the behavior with the expression that you see there. So it involves both S and B in a combination. So I'm not going to tell you exactly how this is done. I want you to think about it and think about the ideas we had before. Involves setting up and solving some linear equations. So hit pause now and work on it. And if you can make it through this, there ain't nothing you can't do. And so as you can see, there's a lot here, so it's going to scroll slowly. but we form the equations up above, and we just plug in the known values for S and B to get G. We set up the matrix, we find the normal equations, we go through, we solve, and we have our best approximation. Okay, so it doesn't matter if you have 2 variables, 3 variables, 4 variables. This procedure always works, and so you're really getting a lot for your money here, and you're welcome. Okay, so a quick thing that I noticed as I was looking over this, the thing that I was calling y in the previous videos, for whatever reason I designated it with a small x here. It of course doesn't matter. You could use your first initial if you'd like. Unless your first initial is beta, that's kind of weird.
Okay, so that's pretty much all we have for now, and hopefully that you've seen exactly the power of this theory, right? The sky is the limit, as I know I've said before, and you can do all sorts of modeling using linear algebra. So that's all we have for today. So I hope you're enjoying the video more than I'm probably enjoying jury duty, and I will see you hopefully on Wednesday.